Hello people, today we're gonna start Poisson distribution. Firstly, let's relate Poisson distribution to the exponential series. Now we all know if we expand e to the power x, we're supposed to get this kind of a series, 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. If we replace x with lambda, we can write e to the power lambda. Since 1 equals lambda to the power 0, we can write it lambda to the power 0. We want to keep everything like similar. So lambda to the power 1, lambda squared over 2 factorial, lambda cubed over 3 factorial, lambda to the power gamma over gamma factorial, and so on, right? Now, if we divide this if we name this equation to be 1, dividing 1 with e to the power gamma, on the left side we get e to the power gamma over e to the power gamma, which is 1. The right side we get lambda to the power 0, e to the power minus gamma, plus lambda to the power 1, e to the power minus gamma, plus lambda squared e to the power minus gamma by 2 factorial, and so on until lambda to the power gamma e to the power minus lambda by 2 gamma factorial. Now if we take a look at this equation carefully, we see that in the left hand side we end up with a 1, right? We know that total probability is always 1, so from here we can conclude that these values, these coefficients can be thought of as probability. So this entire equation can be thought of as a probability distribution function. So if we say that x is a random variable, x takes on discrete values probability, x equals x takes discrete values 0, 1, 2, 3, lambda to the power x, e to the power minus lambda by x factorial, right? Here we have lambda to the power 0, e to the power minus lambda by 0 factorial, lambda to the power 1, e to the power minus lambda by 1 factorial, and basically the probability distribution function here is e to the power minus lambda, lambda to the power x by x factorial. This is the probability distribution function for Poisson distribution. So if x takes on Poisson distribution with parameter lambda, this is the parameter. So let's get on with the example here. We have x, a random variable, which falls under Poisson distribution with lambda equals 1.2. If you want to figure out the value of probability of x equal to 3, then we can simply apply this formula as described before. Probability of x equals e to the power minus lambda times lambda to the power x by x factorial. So here we know lambda equals 1.2 and x equals 3, which results in a 0.0867. In a similar way, we can figure out the value for probability of x greater than or equal to 1. Now remember, this is not a cumulative probability distribution function. This is a probability distribution function, which means it's going to give you values for discrete values of x. Right? Probability values for discrete values of x, not like for ranges. X being greater than or equal to 1. You're not gonna get probability of x being greater than or equal to 1 by simply placing x equal to 1 here in this formula. What you need to do instead is figure out some other way to do it. Here we can do 1 minus probability of x less than 1. If we consider this to be our probability distribution curve, let's say this is 1, then we have to figure out this area, including this area as well. So what we can do is we can subtract this value from the total area, which is basically 1. So what we can do is 1 minus probability of x less than 1, which is 1 minus probability of x equal to 0. Again, for Poisson distribution, the random variable takes on discrete values only. So we end up with 0.699, right? Now for the last example, we have probability of x being greater than 3, less than or equal to 5, which means probability of x equal to 4, probability of x equal to 5. Let's say this is our distribution curve, greater than 3, x being greater than 3, which means x lies here, from here to less than or equal to 5, here, which means 4 and 5 only. So if we calculate the values, we end up with 0.323, which is the result. For Poisson distribution functions, if we say x is a random variable, which falls under Poisson distribution with parameter lambda, then for this particular distribution we can say that its mean e to the power x equals to mu is equal to parameter lambda. This is one of the conditions, and its variance, which is also represented as power of x, is also equal to lambda. So this is a very good way of determining whether you can consider a distribution to fall under Poisson distribution or not. If you know the mean and the variance and they're not the same, then you can, or maybe far apart from one another, then you can say that this particular distribution, that particular distribution does not fall under Poisson distribution in any circumstances, right? But if they do, lie close to each other, so let's say lambda equals 12.12 and sigma square equals 12.03, then you can consider this particular distribution to fall under Poisson distribution. Thank you.